Welcome to the Photoelectric Effect Part 2, Physics 250. So what we're going to do today is we're going to do experiments. First experiment we want to look at is current versus potential, or voltage, for both high intensity and low intensity light, and then current versus voltage for two different colors. To do this, you need to download the simulation at this following link. I asked you to do that at the end of the last podcast. Hopefully you played around with it a little bit. So to do this experiment, you want to click on the checkbox for the current versus voltage graph, set the intensity value to high, change the voltage on the battery from negative all the way to positive, and see what happens. What kind of graph? You might need to zoom in on the graph to see a better scale, and then repeat the same thing with low intensity and show what happens. So pause the podcast and do your experiments. Make sure you write them down also. Alright, what did you find out? Well, if you did the high intensity graph, you should have found out that when the voltage was positive, you get this nice constant line, and then it was 0 until you hit some specific negative voltage, and then it changed. Well, why does it do that? Well, at the point here where the current starts to increase, the voltage to turn around the most interjected electrons, you've passed what's called the stopping potential. Any voltage equal to the stopping potential or greater is going to stop any electron from hitting the other plates. Alright, so what you need to do is do the low intensity one. You should have done the low intensity one, the high intensity one. Which graph best represents the experiments? Choose your answer, and we'll come back and talk about why that particular graph is correct. Alright, we're back. The correct answer should have been B, where the high intensity light produces this graph, and the low intensity light produces this graph. Well, why does this happen? Well, with low intensity, there's fewer electrons that are popped off the metal, so the current decreases, and so that means the current is proportional to light intensity. As the high intensity goes up, the current goes up. So it's a linear relationship for current and light intensity. The other thing we found out is that the point at which we start producing current, or potential, is below, I should say the potential is at a point where the electrons stop hitting the other plate, is the same for both intensities of light. Let's look at another experiment now. So here we want to do the simulation for a few different colors with a small forward voltage, and the graph we want to look at is electron energy versus light. And I want you to predict what this graph should look like, and then do the experiment. So which graph is the correct prediction for the experiment? If you did the experiment, it should be jumping out of the page at you. Well, the correct answer is D. The question is, why is it D? Well, we look at this. There is a minimum frequency below which the light cannot kick out any electrons. Even if you wait a whole long time, the electrons aren't going to come out. As the frequency of light increases, or you go to a shorter wavelength, the kinetic energy of the electrons being stopped from popping off increase. So it's a linear relationship. The next question is, what happens if you change the metal of this plate? So you can do this experiment, so I suggest you do that. The default, if you're using the default metal, that is sodium, I suggest you go back and do the same experiment, but change the metal and see what happens. Well, let's talk about what the results are for the experiments. If you haven't downloaded the simulation, I recommend you do it. You can play around with it, see what happens. So, what's the first thing? Current is linear proportional to intensity. If the intensity gets bigger, the current gets bigger. Current appears with no delay. There's not a time for it to heat up to knock off the electrons. The electrons only emitted if the frequency of light exceeds a threshold. The maximum energy the electrons come off with increases linearly with frequency, i.e. the stopping potential gets greater as the frequency gets greater. And the threshold frequency depends on the metal. So how do these compare to the classical wave predictions that we were talking about in the last podcast? Let's look at that. How does the classical compare to the experimental observations? Well, the classical claims we should have an increased intensity and an increase in current. The experiment matches that. Okay, that's good. The current versus voltage step starts is at 0, and then it's flat. Right? The step is a flat step. The flat part matches, but the experiment has a tail of energetic electrons, the energy of which depends on the color, or the photon's energy. The color light, this is the color light does not matter, only intensity is what the classical predicts. The experiment shows a strong dependency on color. Time to take the heat out, current low, and then increases with time. Experiments, electrons come off immediately. There's no time delay to heat up. Summary of what we know so far for the photoelectric effect. If light can kick out electrons, then even the smallest intensity of light will continue to kick out electrons. Kinetic energy of electron does not depend on intensity. Light energy must be getting concentrated / focused somehow. As at lower frequencies, initial kinetic energies decrease, and kinetic energies change linearly with frequency. This concentrated energy is linearly related to frequency, is basically what we mean there. And 2 is the minimum frequency below which light won't kick out electrons. You need a certain amount of energy to free electrons from the metal. Alright, so what Einstein did, Einstein used the photon picture of light to explain observation. Light comes in chunks, particle-like of energy. We call these photons. The photon interacts only with single electrons. The photon's energy depends on the frequency of light. For lower frequencies, photon energy not enough to free electrons. So are there any questions? Do you want to do some more simulations or experiments? I recommend that you do as many as you need to in order to understand the this experiment.